Ready, huh? Yeah, here I think we have 13 or 14 cases of Omicron over the last weekend.
Okay.
Yeah, because some students at university, I think they were having some party or something down south in Victoria. So one had Omicron, and then, there probably will be more cases of Omicron here in British Columbia soon.
Zadab sir?
Yes, sir. Yes, sir.
I think we can start our program. About 90 students have joined.
Sir, shall we start?
The sir seems to be busy talking. We'll start after he comes.
Yes, we can start.
Okay, sir. Okay, sir. Good afternoon, one and all present over here. I welcome you all for the webinar on GSNST, a sky survey to search for astronomical transients using an array of robotic telescope, an inaugural ceremony of Shivaji Space Explore Club, organized by Physics Society and Shivaji Space Explore Club of Shivaji Science College, Nagpur. Before I move further, I would like to request Honorable Principal Professor M.P. Dhore sir to preside over today's webinar. Now, with the permission of Honorable President, I would like to move forward. I find that when you have a real interest in life and a curious life, that sleep is not the most important. Today we have with us as a guest speaker, Mr. Malhar R. Kendurkar. He is an observational astrophysics researcher based in Prince George, BC, Canada. I heartily welcome you on behalf of Shivaji Science College, Nagpur. Dear students, participants and my colleague, as we know that an astronomical survey is a general map or image of a region of the sky that lacks a specific observational target. Alternatively, an astronomical survey may comprise a set of images, spectra, or other observational objects that share a common type of feature. Surveys are often restricted to one band of the electromagnetic spectrum due to the instrumental limitations. Although multi-wavelength surveys can be made by using multiple detectors, each sensitive to a different bandwidth. So surveys have generally been performed as a part of the production of an astronomical catalog. They may also search for transient astronomical events. They often use wide field astrographs as well. So this Shivaji Space Explore Club of Shivaji Science College, Nagpur, from here on will provide a platform and opportunity for the passionate amateur sky explorer and astrophysics lovers to shape their dreams. Taking in account interest of our students, we have arranged this particular webinar. So now I would like to request Honorable Professor and Head of the Department of Physics, S.W. Anwane sir, for the opening address of this webinar. Please, sir.
Good afternoon. Am I audible, sir?
Yes, sir. Yes, sir.
Good afternoon. I remember the great Maratha warrior Chhatrapati Shivaji Maharaj, the king of the soil, and pay my humble homage to the founder president of Sri Shivaji Education Society's former president, Dr. Bhausaheb Deshmukh, at the very outset. Respected principal, today's guest speaker Malhar Kendurkar, faculty members, members of Shivaji Space Explorer Club, students of this department, Dr. S.S. Darokar, who has joined us for this program, and all student friends. Today, we are assembled here to listen to Malhar, who is an observational astrophysicist and is working as President of Prince George Astronomical Observatory, British Columbia, Canada. Malhar is going to talk about Global Supernova Search Team, GSNST, a sky survey search for astronomical transients using array of robotic telescopes. I am very pleased today because Malhar is alumni of this college and is student of this department. He is the one who gave me a first glance at the sky through his personal telescope when he was BSc student of this college and of this department during 2012 to 15. Malhar, your presence in this capacity will be inspiring to our students and making we teachers a pride. This college came into existence way back in 1967, and the college is accredited with A+ grade by NAC Bangalore in the 3rd cycle. Also, this college is bestowed with College with Potential for Excellence by UGC in year 2004. Malhar, I remember a nazm by Iqbal Asher, and इस नज्म का किरदार हमारे स्टूडेंट्स है और हमारा स्टूडेंट मल्हार है. The nazm is as following. I am reciting this for you all. मेरे बेटो मेरी उंगली ना पकड़ो, मेरी ऐनक से दुनिया को ना देखो, मेरे नक्शे कदम पे खाक डालो, मेरे रास्तों से रास्ता मत निकालो, मोहब्बत की नई तकसीर निकालो, बुलंदी की नई ताबीर लिखो, मोहब्बत की नई तकसीर निकालो, बुलंदी की नई ताबीर लिखो, मेरी ख्वाहिश है तुम ये कर दिखाओ, चलो रफ्तार कुछ अपनी और बढ़ाओ, तुमसे पिछड़ने का बहाना चाहता हूँ, इसी में जीत पोशीदा है मेरी, मैं तुमसे हार जाना चाहता हूँ. We want students to excel and go ahead of teachers, and that is what is written in this nazm by Iqbal Asher. So Malhar, you are the role model for students. So we have a learned pass out of our college who is doing very well, and that gives us pleasure and laurels to this college. In future, Malhar will be a helping hand to the budding students of this college. With these words, I conclude my speech, and I hand it over to the comparer, Dr. G.L. Jadhav sir.
Thank you so much, sir. Being a part of this institute, it's been truly a proud moment for all of us. Being a part of this college, I really feel very much proud for having such a wonderful personality, having an ex-student and as a guest speaker. Now, I would like to request my colleague, Dr. Shaheen Sayyed ma'am, to introduce our today's guest speaker, Mr. Malhar Kendurkar. Please, ma'am.
Thank you, sir. Am I audible, sir?
Yes, ma'am.
Okay, thank you. A very good afternoon to one and all. At the outset, I pay my humble homage to the founder president of Shri Shivaji Education Society, Dr. Bhausab Deshmukh. I welcome you all to the webinar on GSNST, a sky survey to search for astronomical transient using an array of robotic telescopes. Today, we are very pleased to have our guest speaker, Malhar Kendurkar, President at Prince George Astronomical Observatory, Principal Investigator at Global Supernova Search Team, British Columbia, Canada, for this webinar today. GSNST, that is the Global Supernova Search Team, is the first sky survey in Canada dedicated to the search for astronomical transients. In 2021, GSNST consists of 10 astronomers from Canada, France, India, USA, and Argentina. GSNST's telescopes are located in France, Spain, Chile, Argentina, USA, and Canada. It is an all-sky survey where the team scans the northern and the southern hemisphere with a cadence of 3 days to search for astronomical transients. such as novae, supernovae, optical counterparts of gamma rays bursts, tidal disruption events, and optical counterparts of gravitational waves. So it's a very pleasant to see the Malhar Kendurkar sir, the chief guest of our today's webinar, and I am taking this opportunity to welcome our today's chief guest. Malhar Kendurkar, currently working as a president of Prince George Astronomical Observatory, principal investigator at Global Supernova Search Team, GSNST, British Columbia, Canada, a past director for 4 years, a national director of Royal Astronomical Society of Canada, and a principal investigator of Global Supernova Search Team, GSNST. Malhar is also an instructor of physics, mathematics, and astronomy at St. Wauxia College in Vancouver, British Columbia, Canada. He is the first person in the history of Canada to search more than 90 supernova in a year. Today, Malhar sir is going to talk about the GSNST, a sky survey to search for astronomical transient using an array of robotic telescopes. I am sure we will be enriched by this webinar. Once again, I welcome all of you for this function, and I have to speak some 2 lines for Malhar sir. Is that आपकी मंजिल वहीं तक है जहां तक आप हिम्मत नहीं हारते. It's totally suitable for Malhar Kendurkar sir, the alumni of our college, and thank you sir. I welcome you in this webinar. Thank you.
Thank you so much, ma'am. It is very well said that if you want to be happy, set a goal that commands your thoughts, liberates your energy, and inspires your hopes. When we are faced with difficult times, as we are now with the effects of a worldwide pandemic, it is easy to get discouraged and lose hope. Hope is a vital component of human existence, and it is needed to find happiness and peace during times that might otherwise lead us to be discouraged. However, there is a formula for turning your dreams into reality, and it isn't dependent on who you know or providing yourself. And the formula is, of course, obviously that goals plus commitment, that will take you to the dreams. So dreams will come true. So without taking much time, I would like to request today's guest speaker, Mr. Malhar Kendurkar, to inaugurate formally our Shivaji Space Explore Club and guide us on this occasion. Please, sir.
Thank you so much, everyone, for giving a beautiful speech, and I really appreciate. It is actually an honor to be here, and I am grateful for the invitation to inaugurate the club and share about who I am and what I do. So. Firstly, I would actually like to inaugurate the Shivaji Science Explorer Club, and I declare that this club is inaugurated, and it is an absolute honor to be here. So I will just share my slides. 1 second. Okay, can everyone see the slides?
Yes.
Yes? Okay, perfect. So, okay, 1 second.
I think, Malhar, it is not visible. Your screen is yet not visible.
Oh, my screen is not visible yet? Now? 1 second. Let me actually get this here. Share.
Yes, now it is in process.
Okay.
It's
Malhar,
visible.
It's
Malhar, I
visible?
want to just
Yes.
interrupt you. Dr. Deshkar has joined. I think your mother was also visible for some time.
Yes.
And it is a matter of really great pride for teachers, parents, that our boy is having a deliberation, which is a leading thing, I guess.
Yes.
Okay, you can go ahead.
Okay, so I am going to share my slides. Okay, can everyone see the slides now? Yes? Okay, so, in today's talk, I am actually going to talk about some basics, firstly, about optical telescopes. Okay, and what are three optical telescopes which astronomers actually use? Okay, and then what are the different uses? Okay, what are the impacts of optical telescopes? Since the first person who actually built a telescope, his name was Hans Lippershey, and we're gonna talk a little bit about that. And then the modern telescopes, we have like big major observatories in all over the world. We're going to talk about that and what are the uses of modern major observatories. Okay, so firstly, optical telescopes. The telescope which Shivaji Science Club, Explorer Club has it. So it's an optical telescope, and that particular telescope, it's called a Newtonian reflecting telescope. Okay, and using the particular telescope, which is at the college right now, the Astronomy Club can actually look at a lot of different things, different objects in the universe, in the space. Okay, for example, comets, some really interesting stars, nebulae, galaxies, asteroids, okay, and planets, moon, obviously. Okay, so an optical telescope. What are optical telescopes? Well, it's basically, optical telescope is a telescope which is actually used to gather and focus light. Okay, so there are optical telescopes. Okay, well, optical telescopes are actually used for astronomy. Okay, and there are many non-astronomical instruments as well which uses optical telescopes. Okay, for example, spotting scopes for people who, spotting scopes can be used for birding, okay, to look at the birds, or binoculars and camera lenses. Okay, so these are all optical telescopes as well. Okay, and when we are talking about optical telescopes, they look like this. Okay, but this is a big observatory and it has a whole bunch of different instruments for different purpose. And this is the observatory here in Prince George, around 25 kilometers away from our house. So most astronomers now, it's funny because, astronomy, people think like astronomy, okay, you actually have to, look through a telescope, right? But now, astronomers like me and my team members, we actually never physically go to the observatory. Everything nowadays is completely robotic. Okay, so we use machine learning. We use lots of coding, Python, to program our telescopes, and to understand a whole bunch of different stuff, like what really the instrument wants us to do, and how the science, the science we actually have to do using the instruments we have to actually program every single bits. Okay, but so this is really high level astronomy. But as of beginner, I started. So when I actually got into astronomy, which was, I think, in 2012, 2010 to 2012, somewhere around that time. So I didn't have access to all these big observatories. So I bought a small 70 millimeter refracting telescope, okay, which I actually used that to look at planets, moons, and some galaxies. So looking through a telescope visually is actually really fun. It's actually way more fun than having the CCD data, the specialized astronomical cameras. Okay. So there are three main types of optical telescopes which we use. Okay, so the first one is it's a refracting telescope, okay, which uses an objective lens, okay, two objective lens and an eyepiece, okay, and then the second one, which was designed by Isaac Newton in the 1600s, which is called Newtonian telescope, okay. So the Newtonian telescope has a parabolic mirror, which is a M1, which we'll call it an M2, which is a flat secondary mirror at a 45 degrees inclination. Okay, and then the light comes in, okay, bounces off from the primary mirror, which is M1, and then goes to the secondary mirror, and then you see an inverted image because it's a mirror. Okay, and that when, with the eyepiece, you have to focus the image, and that focus is actually called a Newtonian focus. Okay, and the third telescope is called Schmidt-Cassegrainian telescope. Okay, which is kind of a complicated design. Okay, so a lot of amateur astronomers, actually, I know, they build their own refracting telescope and Newtonian reflecting telescope. Okay, so you can actually build these telescopes in home. So the Schmidt-Cassegrainian telescope is actually advanced, and these so the short name for Schmidt-Cassegrainian telescope is SCT. Okay, so that particular telescope has one parabolic mirror as a primary mirror, okay, and then the hyperbolic secondary mirror, okay, which will be at the prime focus, okay, and the Cassegrainian focus is always in the then there will be a Cassegrainian focus. So reflecting telescope, Newtonian reflecting telescope, and SCT are, those telescopes are actually used most now for all the research we do. Okay, there are some disadvantages for refracting telescope with the objective lens, and the reason behind that is when you build too big of a lens, the lens actually gets thinner on the edges, so there is a high possibility that the lens will actually break. Okay, so there are actually couple observatories which has really huge, large refracting telescope. So for example, this observatory right here is called the Yerkes Observatory, which has a 40-inch refracting telescope. Okay, so there are, well, this telescope is now used only for public. They don't use that for research anymore, not for science. And so this refracting telescope is really, really good for observing planets in our solar system. Okay, and then the next one we have, so this is this telescope is in La Palma Islands, Spain. So the name of this telescope is Gran Telescopia Canaries. Okay, and so this is a Newtonian reflecting telescope, and this is actually the largest telescope right now on our planet. Okay, so the diameter of the mirror on this telescope is 10.4 meters. Okay, which is huge. Okay, so there is a comparison. There is a person standing right by the telescope. So that's one of the instrument of that telescope. So that instrument right now is on a Cassegrainian focus. Okay, so you can actually, so the advantages of having reflecting telescopes, so you can actually shift the focus on the telescope. So you can actually go, get the focus into a Newtonian focus. And for different instrument, you can actually shift the focus into a Cassegrainian focus. Okay, So, for example, in this picture, the astronomer is standing right by the instrument. So the instrument is at the Cassegrain focus, and it's a spectrograph. Okay, one of the most important instrument if we are doing the science, So here's the telescope, and if you want to compare the size of this telescope, so there is a car on the lower left side, and that's the dome. So it's a huge, huge telescope. Okay, and then the next one we have it's a Cassegrain telescope. Okay, so this particular observatory is called Paranal Observatory. It's in Chile. Okay, and again, this is a very, very large telescope. You can see the person standing under the telescope, and then the telescope is firing those huge lasers. So those lasers are they are not to call the aliens on our planet. They are called adaptive optics. Okay, so they actually create artificial stars to have an excellent guiding when we are observing really, really faint objects in the universe. For example, like early galaxies, right? Or black hole in our Milky Way galaxy, right? So those adaptive optics actually clears the atmospheric turbulence, because when there's a sudden change in the atmosphere, it actually so there is a lot of turbulence when there's a change in the temperature, right? So those lasers actually helps keeping the turbulence low. Okay, so there's a technology for that. And if the telescope loses guiding star when taking pictures, so those lasers actually create artificial stars to have better guiding. Okay, and these are that's a very large telescope, same observatories. And here's one of the instrument, which is it kind of looks like a transformer from the movie, but it's actually an instrument. Okay, it's called MUSE, Multi-Unit Spectrograph Explorer. Okay, so that is the instrument astronomers actually used to confirm the Sagittarius A star, which is a black hole at the center of our galaxy. Okay, so they did, you can't really see a black hole, but they actually saw the stars orbiting the supermassive black hole. Okay, so when we are actually, I'm talking about telescopes and everything, but so the small telescopes, when early astronomers like Hans Lippershey, Galileo Galilei, Isaac Newton, okay, when they built the telescopes, and they didn't just build the telescope, they also did an excellent work in physics. Okay, so early telescopes have even the smallest telescope, which Galileo Galilei actually used to look at the heavens. When he pointed his telescope in the universe, it literally gave us a different view of the way we look at the universe. Okay, and because there were lots of different theories around Earth being center of the universe and everything around our Earth, everything orbits our planet. Okay, this theory was by Aristotle, right? But early telescopes have actually showed us that Earth was actually not the center of our universe, right? Copernicus model. Okay, and then Galileo Galilei proved it, like, okay, the Earth is actually not the center of our universe. Okay, and when Galileo Galilei pointed the telescope at one of the brightest stars, which he thought they were. He discovered planets. He discovered, confirmed those planets. Okay. Then he saw asteroids, comets. Okay. So this is the telescope which Isaac Newton actually built in 1600. So this is a first Newtonian reflecting telescope which actually uses mirrors. Okay. And you know, astronomers, government, space agencies, private agencies, they have been actually spending a lot of money in this field, in astronomy, astrophysics. Okay, so you know, we have been actually spending billions and billions of dollars now. Okay, why? Well, we are, you know, when we are actually building these large building-sized telescopes, you know, we are actually discovering extremely remote and high redshift stars and galaxies. Okay. And we have also discovered the largest black holes in the universe, which is called TON 618. Okay. So that black hole has a mass of trillion times the mass of our black hole. Okay. So it's in a quasar, which is a very, very active galaxy. Okay. Which is pointing directly towards us. Okay. And quasars are actually one of the brightest object and one of the most energetic galaxies out there in the universe. Okay, and big telescopes, technology, actually, if we didn't have technology, we really wouldn't have discovered all these things or known all these things we know now. Okay, so thanks to Edwin Hubble and Fritz Zwicky. Okay, so you know, we can, when we actually look in the past, so telescopes, you can actually call telescopes as a time machine, really, because your telescopes are actually helping you look back in time. Okay, so in the universe, it's funny, okay, because we actually see everything as it was, not as it is. Okay, everything you see in the universe is in the past. Okay, for example, if I'm talking about, hey, I discovered a supernova which was 350 million light years away. Okay, so I'm talking about that supernova, that star actually died 350 million years ago. Okay, and I captured the light of it, of a dying star. Okay, but at the current stage, there is completely something different in that galaxy. Okay, then we can also try to prove the Big Bang. Okay, but there are a lot of challenges to observe in that much past. Okay, so unfortunately, we can only see 4% of the total universe, and 96% of the universe is still out there to explore. Okay, does anyone have a question? Does anyone have a question so far? Okay. Then we can we can see exoplanets, okay, which is basically life in the universe, okay? Because, you know, in our own galaxy, so we live in a galaxy called Milky Way galaxy, okay? And in our own galaxy, we have more than 100 billion stars, okay? And one more interesting fact, actually. So one of the theory suggested that there are more planets in our galaxy than stars. So let's say we have 100 billion stars in our Milky Way galaxy. So there might be 150 billion to 200 billion planets in our galaxy. Okay. So in who knows, maybe 100,000 planets might actually have life. Okay, so that's why And we have actually telescopes which were, which have been sent in space. Okay, for example, TESS, Transiting Exoplanet Surveys, Transiting Exoplanet Search Survey, or something like that, TESS satellite, or Kepler Space Telescope. Okay, so Kepler Space Telescope ran its mission for 12 years and discovered 1,500 to 2,000 planets. And out of those 2,000 planets, 75 were Earth-like planets. Okay, so there's a high possibility that we will actually, in the next decade or two, we know for sure that we will actually find life in the universe. Okay, so there is a program, there is an organization, nonprofit organization, based in the United States actually. So it's called SETI, the Search for Extraterrestrial Intelligence. Okay, so they don't really use optical telescope. They use radio telescope to detect the radio waves coming from the from the planets. If there is a artificial radio signal. So their radio telescopes are actually one of the most sensitive radio telescopes out there to detect the artificial signals in the universe. Okay, and they have actually discovered a couple of them. Okay, just like one of the signal is called WOW signal. So I don't know what year it was discovered. I think it was 1998 or something like that. Using Green Bank Radio Telescope in West Virginia. So that signal, they know for sure, was actually from some alien planet, some artificial. It was an artificial signal, okay. And there are ways that radio astronomers can actually, tell that, okay, well, that signal was actually an artificial signal. Okay, so they have to do a whole bunch of like data reduction and so forth. And excuse me. So other uses of modern telescope is, astronomical sky surveys. Okay, so when you think of astronomers, using big telescopes. So most astronomers, what they do, they point in one part of the sky, okay, and they'll study one or two objects in the entire night. For example, right now we have 15 hours of night, okay. So some of my colleagues, so they will actually study only 2 or 3 objects the entire night, okay. But sky surveys, so it's actually a survey, okay. So what we actually do is we point our telescope all over the place, okay, meaning everywhere in the night sky, okay. So it's actually, so we call it as a systematic sky survey. So there is a, there is a way to actually scan the sky, okay. But there are people who actually just point the telescope anywhere they want, okay, in the sky. So one sky survey called Dark Energy Sky Survey. Okay, so that sky survey is actually looking for dark matter and dark energy in the universe. Okay, so supposedly dark matter. Okay, so dark energy is completely different than dark matter. Okay, however, we don't really know what these things are because we don't have enough evidence. Okay, but theories actually suggest that these two things are actually holding everything together. Okay, because some of the theories which were actually proposed about the universe, were actually wrong. Okay, so our understanding of the universe was actually completely wrong, unfortunately. Okay, so now the theories are, so the farther away we actually look in the universe, okay, the faster so the farthest galaxy, when we look at the galaxy which are really far away, okay, let's see high redshift galaxies, or maybe the galaxy is 13 billion light years away, okay, which is almost the current age of the universe. So those galaxies are actually moving really, really fast, really faster, okay, away from, they're moving away from us, okay, at a very, very high velocity, okay. And what will happen to those galaxies? They will keep moving away from us, and at one point they will disappear, meaning it won't be visible to our it won't be visible to the instruments. Okay, so we won't be able to see those galaxies. So, and this is all happening because of the dark matter and dark energy. Okay, so there's, you know, a lot of part which we don't understand about dark energy and dark matter, so we are actually still struggling to understand, like, what really dark matter and dark energy is, right? And then there are surveys for dark matter and dark energy. Then there are astronomical transient surveys, okay, which are particularly focused on transients, okay. So transients are, so, even in my talk, I said GSNST, a sky survey to search for astronomical transients. So what really are astronomical transients? So these are very high energetic events which are happening in the universe, okay? But the transients could be really anything. The astronomical transient, in simple words, I could say the objects which actually vary their light. Okay, sometimes they disappear, sometimes they appear. Okay, so we'll actually get into that in a few moments. So there are a lot of sky surveys, okay, out there right now. Right now. So the first one is called SDSS, which is a Sloan Digitized Sky Survey in Apache Mountain in New Mexico. So this sky survey has been going on for 11 years. Okay, and so these guys, right, at SDSS, they're actually creating a three-dimensional map of the universe, and so this sky survey actually helped a lot of cosmological theories. Okay, because before we thought, okay, that universe is just a flat plane, like 2-dimension or 1-dimension, okay. But the kinematics of the universe, our thought and our theories were actually completely wrong. So universe is actually 3-dimension, okay, but we really don't know the shape of the universe, okay. We actually will never know the shape of the universe because we don't know what is the center of the universe. Okay, we see universe as a 3-dimension. Okay, then another sky survey is called ZTF, which is from ZTF actually started in Caltech. Okay, it's called Zwicky Transient Facility. So it's actually named after Fred Zwicky. Okay. He's actually the person who started this branch of astronomy, okay, astronomical transients. Okay, however, astronomical transients is actually a broader topic called time domain astronomy. Okay, so then there's another sky survey called Assassin, which I was actually employed. I was working with Assassin. So it's called All Sky Automated Survey for Supernovas. And then there is a Gaia space mission, which is run by European Space Agency. And then we have Hubble Legacy Sky Survey. So Hubble Legacy Sky Survey was actually one of the most interesting sky surveys because the Hubble Heritage team at Space Telescope Science Institute in California, they were actually trying to look for the most distinct galaxies, Okay, and that's how actually they discovered the Hubble Deep Field. Okay, so a single tiny part of the sky, which is, let's say, maybe, 30 pixels by 30 pixels. Okay, and there are more than 10,000 galaxies in that tiny part of the sky. Okay, and then Hubble Heritage team started doing that for the entire sky for 10 years, and they found just galaxies and galaxies, nothing else. Okay, and the results, which they published in 2013, that they said there are more than 100 billion galaxies in the observable universe. And remember that number, observable universe is only 4%. Okay, there is 96% which we can't observe. So 100 billion galaxies in the observable universe, and more than 100 billion stars in each galaxy. Okay, so the universe is big. Okay, and then there's my sky survey, GSNST, which we focus on astronomical transients, including supernovas, gamma ray burst, optical counterparts of gravitational waves. We also look for novas, which are, so when our sun will die, it will actually die in a nova. Okay. And we also study variable stars. Okay, so variable stars are the star who actually change their luminosity, brightness, okay, in particular amount of time. Okay, and then there is a pan stars, which is a survey for asteroids, comets, and supernovas. Okay, pan stars searches everything. And then there's LSST, which will be coming online pretty soon. I think 2022 or 2023, which is called Large Synoptic Sky Survey. Okay, and then there's Euclid Space Telescope. So Euclid Space Telescope was also a mission of European Space Agency, looking for I think they were looking for high gamma ray particles, gamma ray burst. So you guys are probably wondering, like, I'm talking about sky surveys, okay? But why do we actually survey the sky? What is the importance, of survey the sky, and what is the importance of scanning that much sky and having that much data every single night? Okay, well, there are actually lots of important, and in 10,000, and let's say in 100 supernova discoveries, one supernova can actually give us the information which we actually didn't had in the past about the universe. So each supernova we discover could be actually an important discovery, because you never know. You can actually find some really, really cool supernova which will be a new type of supernova. Okay, so I'm going to explain what supernova is in a few moments here. Okay, so excuse me. So the main reason for surveying the sky, okay, is to search for transients, okay, such as novae, supernovae, gamma ray burst, and optical counterparts of gravitational waves. Okay, and also to know the intrinsic and extrinsic details of any astronomical object. Okay, for example, variable stars. Okay, and there are different variable stars, intrinsic and extrinsic. Okay, so some of the variable stars are going through physical change, okay, in their core. Okay, so there's a mass transfer happening inside the core of the star. Okay, So those particular stars are actually called delta Scuti. So from one side they're actually expanding, and from other side they're actually they're shrinking. Okay, so those are really strange type of stars. So in 2017, actually, I discovered one of the star like that. So the name of that star is GSC 0762-2924. So those are coordinates. Okay. And, another major reason to survey the sky is, in contrast to studying a single object in the space, we are, producing tremendous amount of data. Okay. And right now, GSNST, our sky survey data is not public yet. Okay, so we're gonna actually do a data release in a year or two, because it's a lot of data. So every night we usually get more than 20 to 50 gigs of data. Okay, so and over for 3 years, so we have a lot of data, and we want to make that data public so everyone can actually access the data, and they can find some very, very cool stars or an asteroid. Okay, and finding, so supernova is actually it's one of the most important object to study in our night sky. Okay, because type 1a supernova, okay, which I will explain soon, actually helped us understanding that the universe is actually expanding. Okay, and it's not stopping. Okay, it's expanding faster and faster each second. Okay, so type 1a supernova actually helped us understand how the universe is actually changing. Okay, and it also, well, some particular rare supernovas can actually help us understanding the formation of the universe too. Okay, so here's what so a kind of a overview of Global Supernova Search Team. Okay, so it is the first sky survey in Canada, okay, dedicated only to search for astronomical transients. Okay, and so we started this team in 2018 August. Okay, so from Canada, and my colleague and a friend from France. Okay, so first in 2018 we scanned, meaning we observed the northern hemisphere. Okay, because I live in north, 54 degrees north, and there is a lot to observe in the sky. Okay, and excuse me. So GSNST actually grew in capacity by 3. Okay, in 2019. Then we had 5 astronomers from United States, India, and Argentina. Okay, and in 2020, last year, GSNST became an all-sky survey, okay, covering both southern and northern hemisphere, meaning we observe the sky, both the entire northern hemisphere and southern hemisphere. Okay, so we have more telescopes in north, but we have only 3 telescopes in southern hemisphere. Okay, but that's enough to cover the southern hemisphere. And now we have 10 astronomers in 2021 from Canada, France, India, USA, and Argentina. So and most of the astronomers here in GSNST, they have their own instruments and very expensive cameras. okay, to do science. So how do we really survey the sky? Okay, we need, specialized instruments. Okay, so first, here in Prince George, we have a wide field survey camera, which is on our 0.6 meter telescope as a part of GSNST. So right here is our telescope in Prince George. Okay. So I have observed also 75% of the Northern Hemisphere using this telescope. Okay. And in 2018, since 2018, actually, this telescope has discovered 17 supernovae and 3 novae in Andromeda Galaxy, which is the closest galaxy to the Milky Way. Okay. And limiting magnitude, meaning, so in astronomy, the things are a bit weird, or I shouldn't say weird, they're kind of opposite to the, real world. So when I'm talking about magnitude, okay, it's the brightness, okay, the flux of an object. Okay, let's call it brightness. Okay, so when we are actually calculating the brightness magnitude in the minus, for example, the brightness of the sun is minus 26.72. Okay, so when you go into minus, the object actually gets really, really bright. Okay, and when you go into plus, okay, the object gets fainter and fainter. Okay, when you cross the 15 magnitude threshold, then the object starts to get really faint. Okay, so 21 magnitude is 21,000 fainters than a human eye can actually see. Okay, so that's really, really faint. Okay, and we are actually discovering 21, 22, even 22 magnitude supernovas using different telescopes. Okay, so we are actually only, so GSNST and Pan-STAR Sky Survey are the only 2 surveys which are actually discovering those supernovas at 21 and 22 magnitude. There are no other sky surveys which are actually doing that. Okay. So other main telescope which we use. Okay, so we call these follow-up telescopes, follow-up observatories. So the first one is in northern Spain. So so that's a refracting telescope. Okay. The second one is in southwest France. Okay, so that's a Newtonian reflecting telescope. Third one is inside a dome in Chile, which is a 17-inch. The type of the telescope is it's a type of a SCT, Smith-Cassegrain telescope, which is called Tall Kirkham telescope. And then we have 4 Slow Canary Islands Observatory, which has 20-inch and a 17-inch telescope. Okay. And then we have, a 0.4 meter telescope, 20-inch telescope in Arizona Sky Village. Another 0.5 meter telescope in Osayus, British Columbia. And one in Quebec, Canada, again, 14-inch Celestron telescope. One remote telescope in Arizona, Benson. And another 14-inch in Quebec. So these are all our sky survey telescopes, which some team members actually use to take the follow-up of the discoveries. Okay, and some of the team members actually use the telescope to get the spectra of the discovery. Okay, meaning to classify what type of astronomical transient is. Okay, so these are the locations of our observatories. So this is called a sky coverage map. Okay, so sky coverage map, meaning how much sky, excuse me, we are actually covering. So that's pretty much the entire sky. Okay, so in the cadence of 3 days, meaning every 3 days, we are covering 100% of the northern hemisphere and the southern hemisphere. Okay. So here are some of the details of how many galaxies we have actually scanned, meaning took pictures of. So there are more than 14,000 galaxies since 2018 we have taken pictures of in northern hemisphere and southern hemisphere. Okay, and to date, today I actually changed this date today about discoveries. So so far we have 199 supernova discoveries. Well, astronomical transient discoveries. So in those 199, there are gamma ray bursts, novae, supernovae, all type of different things. Okay, so continuous scans in the cadence of 2 to 3 days. So that has actually kind of changed. Okay, because in Spain we have the La Palma volcano is still erupting. So the telescopes have been offline for 85 days. Now they opened up since 3 days, and in 3 days I found 8 supernovas. So we are surveying the northern and southern hemisphere every possible clear night down to magnitude 19 to 22. Okay, so we point all our telescopes for 300 seconds for each target. Okay, and throughout the night we have more than 200 targets. Okay, 200 depends. Okay, depends on the sky conditions, depends if the moon is out, because when the moon is out, it messes up everything. Okay, I mean, sure, moon it's beautiful, good to look at, but moon actually washes out the stars and faint objects. So so here's a discovery map. So this is not a final version of the discovery map. I still have to add a lot of discoveries here. So this is actually one of the rough version I actually made. So this was actually from the paper which we have been actually working on. So hopefully the paper will be published in January or February, hopefully. So here you can actually see in a discovery map the transient which we have discovered. They are all over the sky. Okay, not in a particular area, not in a focus on one area. They are everywhere, they're so well spread out. Okay, so that's the main major reason of doing the survey, of having an astronomical survey. Okay, you're actually having a good sample of the universe of supernova discoveries, and using that huge sample of discoveries, you can actually learn that how many supernovas are actually happening each second, and the distances of the supernovas. Some of the supernovas could be really rare and very interesting. Okay, so GSNST early science results. So how our data actually looks. Okay, so here's a picture of one of my discovery from last year. So in this picture, what you're actually seeing is, so there is a galaxy, and if you guys can see the red marker, okay, so there's a DSS archival image, meaning the old picture, which you cannot see anything in that old picture on that marker marked position right here. And here in our sky survey data, something showed up, and that was actually a very, very extremely young supernova. Okay, I see there's a question. Okay. Okay. So, this is only a tiny sample of what we have actually worked on and have been working on since 3 years. Okay, here are a couple more discoveries from last year. So we also look for quasars, okay, flares from quasars, meaning the black hole in the center of that galaxy is getting active, okay, and it's throwing off huge jets, okay, plasma jets, which are actually traveling close to the speed of light, okay. And then our data can also, as a citizen science project, anyone can actually go through our data and find their own variable stars. Okay, so of course, I mean, the person will actually have to understand what variable stars are and what all these values actually mean. The mass, how to calculate the mass ratio of the star, and BV index, the color of the stars, and so on and so forth. So I've been talking about mostly supernovas so far, and so what are supernovas? Okay, we have a now you guys probably have a hint, like, okay, it's an explosion. Okay, one of the largest explosion in the universe, most energetic explosions. Fine, okay, but there is, what really is a supernova? Okay, so, well, a supernova actually, occurs upon the death of a certain type of star. Okay, certain types of stars. Okay, not our sun. Our sun is not big enough. Okay, our sun will never go into a supernova. Okay, so a star, if a star has to go, if a star goes into a supernova, so the star it should be at least 30 times the mass of our sun. Okay, so the word supernova was actually coined by Walter Bade, okay, on the left, and Fritz Zwicky. So Walter Bade and Fritz Zwicky were actually colleagues. They used to work at Caltech. Okay, and Fritz Zwicky actually is the person who actually started the Zwicky Transient facility. Zwicky Transient, it's a survey. Okay, so in that picture right here, you can see that Fritz Zwicky is actually sitting on the ladder and looking through the spotting scope on an 18-inch telescope at Palomar Observatories in California. Okay, so that was his old telescope in 1970s and 80s. Okay, now if you look at ZTF's Zwicky Transient Facilities telescope, it's this one. Okay, completely changed. Everything is new. 1.6 meter telescope. Okay, and this is actually the leading survey on our planet to look for supernovas. Okay, everything you see in this picture is a robot. Everything. Okay, not the person who took the picture, but everything. There are absolutely no humans in, working on the computers or looking through a telescope. Okay, so it's actually pretty incredible. So you can see, since the telescope were built in 1500s by Hans Lippershey, and now here we are, that we don't even need humans to look through our telescopes anymore, because machine learning and artificial intelligence can do that. Okay, so how a supernova looks in real life, if you see one, well, here it is, one of the picture of a supernova called SN 2017 EAW. Okay, so SN stands for supernova as an acronym. 2017 is the year it was discovered, and then EAW is the alphabet, so it goes from AAA and then AAB and so on. Okay, so every year, Sky Surveys actually discovers, the total number of supernovae each year discovered is more than 15,000 supernovae every year. So that's a lot. That's a large number. So you can imagine how many stars are actually dying every day in the universe. Okay. So what causes a supernova? Okay. So a supernova happens, where there is actually a sudden, there is a change, in the core of the star, meaning the nucleus of the star, and that actually change can happen in two different types, which can actually result a supernova, So there are actually 5 different types of supernovae, and well, the other 3 we actually don't really understand them well because there is not enough evidence. Only 1 or 2 supernovas actually have been found for those kind of different and weird type of supernovas. So the common ones are type 1a. So what is a type 1a supernova? Well, it actually happens in a binary star system. Another thing, so in the universe, or in our galaxy, let's say, 50% of the stars actually come in pairs, and 50% stars are single star systems, meaning in pairs, it's more than one, 2 stars, or there are sometimes quadruple star system. So type 1a actually occurs in a binary star system. And these are the most interesting one because remember, this kind of supernova actually tells us the expansion of the universe. And when we actually discover this, we can actually calculate the velocity of the radial velocity. So this happens when binary stars are 2 stars orbiting one another, as the name says. And so in type 1a supernova, so there is binary star, and one star should be a white dwarf star. White dwarf stars are small but deadly, dangerous, very, very dense. And one is white dwarf, and other star of a binary star system could be really anything from a giant star to even a smaller white dwarf. It could be really anything. So like I said, white dwarfs are dense, so they have more mass, and more gravity. So they actually steals matter from its companion star, And when the white dwarf star actually gets full, it cannot actually really handle anything anymore, And then guess what happens? The white dwarf actually explodes, explode and resulting into a supernova. That's what type 1a supernova is. So here's the remnant of type 1a supernova. It's called a ring nebula. And when a star explodes, it actually pushes out all its hydrogen, helium, and other ionized gases. And you can actually see that in the spectra on the bottom of this picture. There is hydrogen alpha, hydrogen gamma, beta, then helium, and hydrogen delta, and so on and so forth. Right?
Malhar sir, sorry
Yes.
for interrupting. if you could end up the session within 5 minutes, so we would have some interactions with students as well.
Yes, yes,
That would be better for us. Yeah,
yes.
yeah. Please.
So white dwarfs it's a very dense star. Okay, and its mass is, the mass of the white dwarf is comparable to the sun, comparable to that of the sun. Okay, and the volume is comparable to the Earth. So you can see that white dwarfs are really, really dense. Okay, here's the comparison of sun and white dwarf. Okay, so there's a sun, and on the right side, there's that tiny white dwarf. There it is. Okay, so it's pretty interesting how deadly white dwarfs are. And this is a picture of another supernova. So type 2. Okay, so type 2 supernova actually occurs at the end of a single star's lifetime. Okay, and these are another interesting supernovas, which so the star actually runs out of nuclear fuel. Okay, and some of its mass actually flows into the core of the star. Okay, and when the core actually gets too heavy, it actually gets destabilized, unstable. Okay, and this process happens really fast. Okay, so this type of supernova is also called a core collapse supernova. Okay, and for this supernova, the star must be at least 40 to 50 times the mass of our sun. So, and why study a supernova? So supernova actually burns only for a short period of time. Okay, but it can actually gives a lot of information about our universe, such as expansion. Okay, expansion of the universe, and by discovering the high redshift supernovas, it can actually give us the formation of the early galaxies. Okay, and so we report all our discoveries publicly. Okay, they are available for public to see, and we report on a website called Transient Name Server. Okay, so it is actually run by International Astronomical Union. So here's a small graph of GSNST discoveries. So blue ones are supernova discoveries, and red ones are false positive, which we actually don't report the discoveries anywhere. So today, GSNST, we are actually developing a transient search pipeline, okay, automated pipeline, okay, and to date, in 2021, so far I've discovered 83 supernovas, and the target is 100. It was 200, but I changed it to 100 because I know I can't get to 200 right now because it's almost end of the year. And we are also looking for research grant to set up robotic telescope in northern British Columbia, to advance the search for supernovas and GRBs. And in summary, we will progressively survey the sky in both north and southern hemisphere, hoping to discover more rare supernovas. Okay, and yes, so we will actually make the data available for public very soon, hopefully by next year. Okay, and everyone can take a part in this project. And I'm open to have I'm open to take projects as well. Okay, so that's okay. Any questions?
Dear students and participants, now it's time for interaction session with our guest. If you have any queries, questions, please, you just go ahead. You just unmute yourself one by one and ask your queries, please.
Hello, sir. Hello, Malhar, sir.
Hi.
I'm Roshni Pahuja.
Hi,
and I'm
nice
not
to meet you.
wishing you any afternoon because I know you are in some different time zone.
Yes.
And I am also a graduation student from this college itself. So that makes you my super senior. And my question is to you. Personally, I would say you were the geology student in this college. Then how did you find your interest in astronomy?
Well, because I was actually, well, I was, that's a good question. So I was a geology student, yes. And so I actually had interest in astronomy since, I was a kid. Okay.
Okay.
But so when I was in Shivaji Science College, so in my physics course, first year physics course, I actually had a topic on the first chapter or second chapter was on astrophysics, introduction to astrophysics. Okay. And then when I, started doing that chapter in physics, then I thought, okay, well, I want to actually do. So I actually developed my interest more when I actually started doing the astrophysics chapter in our physics course at Shivaji Science College. So
Okay, that's very nice to hear. And also, sir, about your own discovery, it was very inspiring. But how did you discover the pulsating star? Is it rare something?
so for the pulsating stars, that's a great question. So you actually have to learn the light curves. You have to actually look at the light curves. Okay, meaning, so we take hundreds and hundreds of pictures of the same star. Okay, and then you have to do the magnitude calculation of the of those pictures. Okay, and when you do that, you can actually see that the brightness of the star is actually changing in, let's say, 2.5 hours, 0.092 days. Okay, and when you do that, you get text files. Okay, and you plot those text files, and you can see like beautiful curves. Okay, in your graph. Okay, so a lot of bright pulsating stars have already been discovered now because of the other sky surveys, but the stars which are 13 plus magnitude, they are still yet to be discovered. And our sky survey actually allows everyone to actually discover those 13 plus magnitude stars, because we actually go in the same region of the sky time to time. So, but we just don't have enough time to really analyze that big of a data.
Okay, so that was great. So actually, you might have designed any type of telescope by your times, right?
Pardon me?
You must have designed any type of telescope, right?
No, I
Not even a
no,
single one.
no, no. I was actually planning to, but I just never got around it. I actually wanted to do it. I wanted to build a telescope, but maybe in a couple of years, or maybe next year, or maybe in Christmas break.
I might be looking for that in the Google, okay, in newer times.
Yes.
Yes, sir. And actually, I am thinking of designing a Cassegrain telescope. So I would like your tips about that.
Yes, absolutely. Yes, that's Cassegrain telescope. Absolutely. Definitely, I can help you.
So can you share some of the details? Where should I start from?
So firstly, you'll have to get parabolic mirror
Okay.
from one of the stores. So I know one person in India. His name is Raju Patel. He lives in Mumbai. So he
Okay.
has a website called here. I'll actually share it. www.com. So hopefully that website works. So he has parabolic mirrors in his store, and or you can actually build a mirror by yourself as well. But
Tejraj. Some name was crashing. Tejraj.
Okay.
Tejraj.
Tejraj, yeah.
Some supplier from Pune.
Yes.
So that's very
Yes.
generous of you for sharing.
Yes, not a problem. So, and yeah, and then you have to decide like how big of a mirror you want, right? But mirrors
Magnification.
are how much?
Magnification around you suggest would it be suitable for me? Which magnification would be suitable for me?
Well, so the basic, I'll say around 5 to 6 inch telescope, it's good for the start.
Okay.
Okay, and nowadays the thing is, building telescope is actually more expensive than buying it.
It is. Yes, it is. But it makes a person creative, right?
It does. It does. Yes. And Cassegrain telescope is actually really fun to build. Okay, because couple of our observatory members here in Prince George, they have actually built a Cassegrain telescope, and you do get really good results from that telescope, right? The pictures are sharp.
Okay. So, is it possible that I can have all the arrangements of refracting telescope, Newtonian telescope in one telescope? It is a
Um,
silly idea, but is it possible?
I don't know. That's
And it's very
no,
complicated.
because it will be really complicated because for refracting telescope, you're actually using the lens. And
Exactly.
Cassegrainian, you're using, two mirrors, and for Newtonian, it's again two mirrors.
Mm-hmm.
Right? Then if you do that, then you'll actually have a lot of it will be too complicated as a design.
Okay. Okay, that is considerate. Okay. So, last question.
Yes.
So, you showed the design of the Cassegrain telescope, and
Yes.
the concave mirror there was converging. I think it should be diverging, right? But it converges in the Cassegrain arrangement.
It does. Yes, so it's
I
a
see.
hyperbolic mirror because it actually gets when you have a hyperbolic, it actually gets the focus into a back focus, meaning the prime focus. Okay, so that's the specialty of having a Cassegrainian telescope. So you can actually fix a camera. So those kind of telescopes are actually called astrographs.
Okay.
Okay, and which are actually specially used for um, taking really fast astronomical pictures of the sky. And so it's actually called a rapid astrograph. Okay. So you can actually attach a camera in front of the telescope. Okay. Not like other telescope in Newtonian, you have to attach the instrument on the right hand side or the left hand side of the telescope, right? Or on the back focus. So in the Cassegrainian, you can actually attach a camera on the front, which is called a prime focus. Okay, or you can also call it as a hyperstar. So that's why.
Oh, okay. Got it, sir. Thank you so much, sir.
Thank you.
It feels really pleasurable to have my answers from all the way from Canada.
Likewise. Thank you so much for asking the questions.
Yes, sir.
Any student want to pose a question?
Sir, I do have a question.
Yes.
Hello, sir. I'm Manoj Gatate. I'm a student of MSc Physics first year.
Yes. Hi.
Sir, as you mentioned, for a star to go through a supernova type 2, it needs to have a mass 20 times as that of our sun.
Yes.
And
Type 2, yeah.
considering our star, it is a single star and it doesn't have enough mass. So what kind of end can we expect our sun to go through when it runs out of fuel?
That's a good question. So what will happen to our sun? So our sun is a small star in the universe. Okay, there are much bigger stars in the universe than our sun. So what will happen when the sun will die? So the sun will eventually expand. Okay, it will get bigger. Okay, and unfortunately, it will actually get bigger. I mean, it will the diameter of the sun will actually close to the orbit of our Earth. Okay, so yes, of course, the Earth won't be alive. No one will be. So when the sun will actually get bigger, and then So it's actually the sun will be at its maximum capacity, okay? And when that happens, the sun will actually start losing its mass slowly and slowly, okay? And eventually, when the sun is losing its mass, it's actually releasing all the major chemicals, major um, yes, elements from the sun, which is hydrogen and helium, right? And eventually, after that, after maybe 100,000 years later, the sun will actually turn into a white dwarf. Okay, and when that happens, then the sun will actually explode, okay, and then start losing its mass slowly and slowly, and then eventually it will turn into a white dwarf, okay, and if if the white dwarf actually, so some of the white dwarfs are very, very interesting. They can actually explode time to time if they have a companion, but it won't really happen anything with our sun like that. But yes, our sun eventually will turn into a white dwarf.
So essentially, it will expand and then contract.
Yes.
So in the initial part, it's essentially a type 2 supernova because
No,
it's
it won't be
expanding.
no, no, our sun won't actually increase its mass. It will increase its diameter. Okay, type 2 supernovas. So the type 2 supernovas should have a mass of at least 20 to 40 times the mass of our sun. Okay, so our sun is not really changing a whole lot of stuff inside the nucleus. Okay, everything is happening in the photosphere of the sun, which is the outer part of our sun. Okay, hydrogen is turning into a helium. Okay, um, and when that happens, well, yes, the core actually gets destabilized. Okay, but the star, if we are talking about particularly type 2 supernova, the star should actually have a very, very high, the star should be a high mass star. Okay, our sun is not a high mass star. Okay, and we can actually see that in a Hertzsprung-Russell diagram, HR diagram.
Okay, sir. Thank you.
You're welcome.
So, anybody else? Any questions?
Yes, there's a question. So my name is Lokesh. I'm a student of BSc semester 3. I have an interest in astronomy from childhood. I have read multiple books of Jayanta Nagar. My favorite topic is quasar, but not other books or web have much information about it. Can you please tell us a little about quasars? So quasars, they are, really fascinating objects. Okay. Quasars are galaxies. Okay, but not every galaxy actually has a very, very active black hole. Okay, that's what makes quasars really interesting and cool. Okay, so quasars have huge, very, very big supermassive black holes. Okay, much, much bigger than our Milky Way galaxy's black hole. Okay, and those black holes are active. Okay, meaning they are constantly eating stuff and then throwing stuff outside from the event horizon. Okay, and also quasars are one of the brightest object in the universe. Okay, so for example, if a quasar is like, well, they're actually one of the most distinct object in the universe. Okay, they could be like billions and billions of light years away, and they could be really bright. Like bright meaning I'm saying like maybe 14 magnitude. Okay, so one of the first quasar which was discovered in 1998 is called 3C273. Okay, using Hubble Space Telescope. So that quasar actually looked like a star. Okay, it had nice diffraction patterns. Okay, but then by getting the spectrum, people saw that there is a huge blue continuum lying in the lines in the spectrum, right? And then they saw that, okay, there's something really strange going on with this, because it was actually throwing off jets. Okay, and it was pulsating, meaning the brightness was actually keep changing. Okay. Um, and again, the Sloan Digitized Sky Survey has found more than thousands and thousands of quasars in the universe, which are at a very high redshift, early formation, early quasars in the universe, and billions of light years away. Okay, so they're actually pointing; those quasars are actually pointing directly towards us. Okay, as towards us. Okay, directly parallel. Okay, if a quasar is the accretion disk of a quasar is pointing, 90 degrees, we actually won't be able to see it because the dust is blocking all the view, okay, in the accretion disk. But if the quasars are pointing directly towards us, then we can see them.
Thank you so much, Malhar. I'm truly overwhelmed. It's been an amazing and wonderful webinar. You just took us through all the details. We really have enjoyed this session very much. Being a faculty member, I was also so much curious about the topic and this astrophysics and all. And I tell you, you have literally created a knowledge right from A to Z for all of us and our students as well. Telescopes, optical telescopes, types of telescopes, and impact and uses of telescopes. You have just taken through the fundamentals of astrophysics. So thank you so much once again for being a part of this Shivaji's Space Explore Club. Thank you so much for giving us time. Now I would like to request our Honorable Principal, Professor M.P. Dhore, sir, to address this webinar. Please, sir.
Thank you, Jadhav sir. Our today's young and dynamic resource person for this webinar, Mr. Malhar Kendurkar, Head of the Department of Physics, Professor Anwane. I can see here Professor Darokar sir attending this webinar in the Department of Physics. Professor D.W. Deshkar is also with us to witness his students to witness his student as a guest speaker. Then all the staff members of the Department of Physics, Professor Jadhav, Madam Dhokne, Madam Syed, and all the teachers of our college and all the students of physics department and all the members of our Shivaji Space Explorer Club. A very good morning to Malhar sir, and good afternoon to all of us. In fact, firstly, I apologize, Mr. Malhar sir, for having or for choosing this very inconvenient time for the webinar. In fact, it's morning 3 a.m., 3 or 3:30 a.m. in his place, and he has been speaking with us since half an hour, and I really thank Malhar sir for enlightening us with this odd time and sparing your night, in fact, with all of us, for all of us. But at the same time, I am happy that Malhar sir, being alumni of our college, he must be very much happy to share his views with the alma mater, with the stakeholders of the alma mater. And the same feeling is with us, sir. We are also happy and taking pride and privilege by having your interaction with all of us. Actually, being a Shivajian, and that too from Canada, you are talking with all of us. It's a very proud feeling for all of us that one of our student is doing wonders in Canada, and he is leading Prince George Observatory in Canada and doing wonders. Because in your introduction, I heard that you have searched 90 supernova in a year, and you are the first one who has searched 90 supernova in a year. So that is a great achievement as far as our alumni and our Shivaji is concerned. So big congratulations for that, Mr. Malhar, and you are doing very good work in terms of observational astrophysics. Still, you are researching on that, and we hope that in the coming years you will be having your PhD at the earliest. And as far as the Department of Physics of this college is concerned, recently in our college we have formed a Shivaji Space Explorer Club under the leadership of Professor Anwane, and under that club we have also procured recently a telescope, and hardly it had been 1.5 months that we have procured that telescope, and as after procurement of the telescope, we are neophytes. Nobody is there to handle the telescope. So it was a great worry for our Professor Anwane that we should have some expertise, and with the consultation of some expertise, we will explore the activities at our Space Explorer Club. And fortunately, he came up with your webinar, and today I found that we were in search of some expert, and we have got our own expert in our family. So that way I am very happy, and must be Professor Anwane is also happy that we have got some expert to advise us, to guide us in this particular front. So again, the credit goes to Professor Anwane and the staff members of the Department of Physics. I congratulate all the staff members of Physics Department for having this particular webinar on this particular topic. And it was really a feast for all of us. It was a very quite general topic, but the interaction which you had with us, that obviously was a good, interesting one. And as we are having a telescope at our college, now we are planning for some more activities under your leadership, and obviously we will be having some MOU with your observatory, and we look forward to have some collaborative work with your observatory and our college.
Absolutely.
And finally, thank you, Malhar sir, for having with us. Thank you for sparing your time. And I take this opportunity to thank all the staff members from the Department of Physics for having this wonderful interaction with all of our students. Also, thanks to Dr. Deshkar sir and Darokar sir. It was nice to see you here. And with these words, I take your leave. Thank you very much.
Thank you so much, sir. It's really been a matter of pride for all of us that one of our ex-students have now been a guest speaker. It's truly a proud moment. My best wishes to Malhar, sir, and hope you will collaborate with us in coming future as well. And thanks for giving us your valuable time. Now we are moving towards the end of the session. Without taking much time, I would like to call upon my colleague, Ms. Roshni Ahuja, to present a vote of thanks.
Hello and very good afternoon to all. Actually, hello and very good evening to all the respected and distinguished personalities, dear students, and everyone gathered over here. It is my privilege to have been asked to propose the vote of thanks for today's program. I, Roshni Pahuja, on behalf of the entire fraternity of the college, first of all, extend my hearty gratitude to our today's webinar speaker, Malhar Kendurkar, who is president at Prince George Astronomical Observatory, principal investigator at Global Supernova Search Team, GSNST, British Columbia, Canada, for illuminating us with his knowledge despite his busy schedule. Also, we are fortunate to have such a renowned identity with us who pursued his graduation from the same college. The point where he told us about his own discovery of pulsating star did really leave a mark on us. Thank you so much, sir. I would also like to thank our principal, Dr. MP Dhore, for giving us permission to organize this webinar session and his continued support in all our efforts. Next, I owe special gratitude to the head of physics department, Dr. S.W. Anwane, for his kindness, hospitality, encouragement, and his leading supervision at every point of time in the college. Also, I extend my sincere thanks to Dr. S.S. Darokar and Dr. Deshkar for being with us today. Further, I express my heartfelt thanks to our today's host, Dr. Gajanan Jadhav, for his efforts towards today's anchoring. I also wish to thank all our teachers present here for their cooperation. Also, thanks to all the participants for attending the meeting. Finally, I leave you with this relatable quote by Elon Musk. When something is important enough, you do it even if the odds are not in your favor. Right. Thank you so much, sir. Thank you.
Before
Thank you,
closing,
Malhar, sir.
Yes.
before closing, Malhar, I would like to invite you somewhere in the mid of January, and there you will be guiding to limited students, MSc second year students, for data analysis. So
Yes.
we
We
will
could.
have a
Yes.
technical session, and we will have, in due course of time, we will have our MOU signed.
Okay.
Under the guidance of our principal, we shall prepare documents, and we'll have that signed.
Okay. Absolutely. So yes, thank you so much for inviting me. It was really great meeting you all and seeing everyone. And excuse me, I really appreciate the. It is an honor to give a presentation for my college. So thank you so much. And I hope to see everyone very soon.
Bye.
Okay. Have a good night. Have a good afternoon. Sorry.
Okay, good night. Bye.
Good
All
night.
right. Bye.
Bye. Bye.